Today, actually, what I thought was, instead of taking a particular software, I thought, how can we understand calculus better using MATLAB? So the agenda today is I am going to handhold and take you to some basic commands in MATLAB. Remember, we are not going to learn MATLAB as a course now. We'll see what are the basic commands in MATLAB, and then from there we will gradually move to calculus. Okay, and this particular year, the last year, the pandemic has opened new doors for us. Okay, actually, MATLAB means what we say, we want to install the software in our system, and then usually we used to work on it. But this pandemic has opened the doors that today I'm going to use the cloud platform. That is, it implies I don't have the software in my laptop. I'm going to use only the cloud platform. Okay, so it is very easy to use that. Okay, so first let me tell you how to use that one. Okay, so that later on I have also shared the code with Srija ma'am. You can get the code from ma'am and you can work and see. Okay, so now let me so if you go to this MATLAB online, okay, MATLAB online, if you type MATLAB online in the address bar, okay, you can see this MATLAB online. So now let me go inside. Okay, so start using MATLAB online. Okay, so now you can give your mail account, okay, and you can log in. Okay, so I'm giving this thing, okay, and I'm giving my password, which I've already have done. You can say, when you go inside the first time, it will ask you to whether to use your Gmail account or a Twitter account or GitHub account. You can use anything and you can get into it. Okay, so I'm just going inside. I hope you can see my screen now. You can see my screen, is it? Okay, so this is my cloud MATLAB window. Okay, so which implies that I am not having this software installed in my system. I don't have the software installed in my system, but I'm using the cloud. Okay, so if you go inside there, you can start a new script file. Okay, it should be a .m file, and then you can work on this. So today I am going to use only this particular platform. So if possible, if you are parallel, you can do along with me. It will be well and good. Otherwise, I have shared the code with Srija ma'am. You can get the code from ma'am and you can practice later. Okay, but remember, it doesn't. You no need to have the software in your system. Okay, that's what I'm trying to say here. Okay, now let me go back to the slides. Okay, so as I said, I'm going to handhold and take you through the basics of MATLAB. Okay, so what is MATLAB? It's nothing but matrix laboratory, because the computations are carried with respect to the matrix and strings and the vectors. Okay, so numerical computations with matrices is easily done using MATLAB. Why MATLAB? Because nowadays, as we have seen yesterday, Sarah has dealt with Sage. Sage is also another wonderful software where you can visualize the mathematical concepts, but it is a open source software. Okay, whereas this is we know this is a proprietary software where you have to get the license and then you have to install in a system, or you can directly use from cloud like this. Okay, so why many people are moving towards? Because most of the research is carried using only MATLAB. Even I and my scholars, they are using only MATLAB for writing codes. Okay, so it is user friendly. Okay, that is, it has graphical user interface, easy to work with, and powerful tool for complex mathematics. Okay, so these three things push researchers towards MATLAB. Well and good, you can also use the other softwares. It's left to the user. Okay, now what are the important aspect in MATLAB is, suppose you are getting a pizza. Okay, so that pizza comes with different combinations. Suppose I want cheese on my pizza, or I can have only some vegetables on my pizza. Those are called toppings. Similarly, for toppings things here, you have to add toolboxes. Okay, so toolboxes plays a very important role in MATLAB. Okay, so the base MATLAB will be there. Suppose if you want to do a simulation in aerospace, then you have to get an aerospace toolbox. Suppose you want to play with image processing, then you have to install or you have to get image processing toolbox. Similarly, if you want to play with optimization, then you have to get an optimization toolbox, and it goes on. So here the idea is the base will be given to you. If you want these toolbox, you have to separately purchase that, and you have to work along with this. So the toolboxes plays a very important role in MATLAB. Okay, if you are interested to explore this more, or if you want to work in a particular domain, then you can think of going for a specific toolboxes which addresses your need. Okay, now coming to the desktop, so once you open a MATLAB, you can see this 4 different windows. One is current directory, okay, one is command window, then workspace, then command history. So the default consists of 4 parts. One is current directory, that is from where you are working, then command window, so where you are going to get your answers, okay, or if you want to type single line command, you can use command window, and workspace tells you what are the variables which is created while doing a particular program, and command history tells me what are the commands you are using inside the program. Okay, so it looks something like this. Okay, see here I'm having current folder or current directory is here. Okay, okay, and this is my workspace. You can see workspace, this is the workspace. Okay, well, once I run a program, variables will be created. Okay, and this is the command history. See, command history tells me what are the commands I have used till now. Okay, then command window is where I can see this prompt, where I can going to get my answers, or if I want to do single line command, I will be using this area. Okay, so the same thing is also available in the cloud also. Current folder is there, workspace is available, command history is there, command window is there. Okay, so we will see how it works when we go to the when we try to solve the concepts using this. Now let me toggle back. Okay, so now the first initial thing is, since it is based fully on matrices, how to enter a matrix. You might know this already, but let me give us just an idea of this and then move further. Okay, so suppose I want to input a matrix 3 1 6 4. Okay, how I can do? See, I have to use a square bracket 3 1, then semicolon tells me I'm moving to the next row. Okay, you can ask, it can be 3 comma 1 also. So 3 comma 1 semicolon means the semicolon tells that you are moving to the next row. Okay, so based on this you can input a matrix. So the same matrix I'm having and in the MATLAB I will run and show you, and these are the basic mathematical operations which we can do: addition, subtraction. Okay, here the 2 multiplication happens because A star B gives you the matrix multiplication. A dot star B gives me the element wise multiplication. That A dot star, when we'll be using, suppose I'm having X some 100 points, some Y some 100 point. Now, so for each and every point I want to do the element wise multiplication. So in that case I'll be going for A dot star B, rather than A star B tells me I'm doing the matrix multiplication or usual matrix multiplication. A dot star B gives me the element wise multiplication. Okay, which you'll see. And similarly division. Okay, A dot slash B gives me element wise division, and here A forward slash B means it tells us A star into inverse of B. Suppose I want to solve a system AX equal to B, I'll be finding X equal to A inverse B, is it? So if I have A, the coefficient matrix, B, the constant matrix, then if we just give A backslash B, it's nothing but A inverse into B. It gives you the answer directly. Okay, so that A inverse into B is done using A backslash B. Okay, A forward slash B is A into inverse of B. A into inverse of B. Okay, so all these are some basics idea. Okay, which I will execute and show once we go there. Next is another beautiful thing is subplot. Suppose I want to view some 3 or 4 or 5 figures in a single window, I'll be going for this subplot. Okay, the subplot. So here what I've done, I have divided my 0 to 2 pi with increment of 0.1. Okay, So from 0 to 2 pi with increment of 0.1, I have created some x values. Now I want to plot some 4 graphs in a single window. So 4 graphs means it has 4 cells, is it? Let me use something like this. Just wait. So I'll be having some 4 cells like this. Okay. So now 2 to 1 is this place. 2 to 2 is this place. 2 to 3 and 2 to 4. So what I'm going to do in 2 to 1, I'm going to plot sin x. In 2 to 2, I'm going to plot cos x. In 2 to 3, I'm going to plot e power minus x. And 2 to 4, I'm going to plot sin 3x. So in such a way, you can extend this dimension also. Suppose you want to 9 figures, it can be 331, 332, 333. It all depends on it. Suppose I need 3 rows, 2 columns. Okay, 321, 322. In such a way, you can create subplots. So subplot gives you an idea to view all your graphs simultaneously in a single window. Okay, because sometimes in your thing we will be using this subplots. Okay, now whatever we have seen now let me try to execute this using MATLAB. Okay, and another important thing which I want to mention is right now I am in a script file. I have stored that as webinar.m. My script file is webinar.m. Okay, now this command, this percentage command tells me you are going to comment this statement. That means whatever follows after the percentage is not executed by your compiler, MATLAB compiler. It implies it is a command statement. You know that command statement, is it? In C you will be using backslash star slash, and in C++ double forward slash, isn't it? All those are command statements. Similarly here I'm going to use percentage. Whichever follows after that is going to be a command with respect to the MATLAB compiler. Okay, now I'm coming into this program. Now what is CLC? Okay, CLC clears the command window. Sometimes if you keep on doing some programs, you'll be having a lot of junks here. If you want to clear your command window, you have to give CLC. Okay, I'm just clearing the command window. So in all our programs by default, I will be having CLC. Okay, I will be having CLC so that it clears the previous executed programs. Now clear all. So what is the use of clear all? Clear all clears all the variables which is available in your workspace. Okay, so whatever variable you have created before, obviously once you create a variable, a separate memory is allocated to it. So I want to release all those, I want to clear all those, means I have to give clear all. So it is a best practice, always give CLC clear all for a program, so which automatically clears your command window, as well as it clears all the pre-existing variables which are in no way connected to this program. It releases its memory space. Okay, so here I'm going to follow always CLC clear all. Okay, okay, so if people are there, ma'am, is there no issue, ma'am? Ma'am,
Sir?
Ma'am, am I going fast? No.
No, sir, no.
Okay, okay, ma'am. So now, as I mentioned there, I'm going to write. Usually, what people do will, for each and every program, they will go to a separate M file. You can avoid that. Okay, in a single C, in a single M file, I've written all the codes. Okay, so that is an easy way of doing it. If you give double percentage, automatically a section will be created. Okay, I'm giving a double percentage here. So before that, a section will be created. I can execute this section alone rather than executing the entire file. Okay, so that makes easy, because for each and every program I don't want to create different M file. Okay, and creating M file is very, very important, because if I give, for example, I'm finding the area of something, means if I give area.m, it won't work, because area is a keyword. Most of the people, we tend to give the file name with what the function we are using. So here you will get a problem. So you can give a general name for your file, and inside that file you can do any number of programs. Okay, so what is the idea here? You have to give double percentage. Okay, now here, as I mentioned, I have given you the a equal to 3164, then I'm calling A. That means I want to see what is the answer. Then I'm finding the inverse of A. INV of A gives you the inverse of A. And B, I'm inputting another matrix 3502. I'm finding the inverse of B. Then I'm adding those two matrices, subtracting those matrices, finding the matrix multiplication, then finding the element wise multiplication, then element wise division, then as I mentioned, to solve the system. Okay, so now let me run this. I see this area is highlighted now. I'm right clicking my mouse. Run section is there. You run this. Once you run this, because I'm not going to get anything from the system, so go to the command window to view your answer. See, in command window, this is where your answer is. So we have given A, matrix A, 3, 1, 6, 4. And what is inverse? We have found the inverse here directly. And what is B? B is 3502. And its inverse is given there. Then C is, we know, A plus B. It is 6, 6, 6, 6. You can see because 3, 1, 6, 4. And 3, 1, 6, 4. And what is the next to me? B, it is 3502. So it becomes 6, 6, 6, 6. So that is C. D is A minus B. Okay. Then E is A star B. That is matrix multiplication. Then F is element wise multiplication. Then element wise division. Then A forward slash B. That is A into inverse of B. And this is the solution of the system. F3, it is A backward slash B. That gives A inverse into B. Okay. So in such a way, you can input your give matrix and you can do the element operation on this. Okay. Now let me move, also do this one. That is, I was mentioning about the subplot. No, I'm trying to plot some 4 different graphs in a single command in a single figure window. So already the code I've discussed there. Okay, now let me run this code. So I'm going to plot sin x, I'm going to plot cos x, I'm going to plot e power minus x and sin 3x in the range 0 to 2 pi. Okay, my domain is 0 to 2 pi. Let me run this. Okay, you can see. So see, I can see the 4 graphs in a single figure window. Okay. So it clearly shows this is the sin x graph, this is the cos x, then this is the e power minus x, then this is the sin 3x. Okay. So in such a way, you can easily view any number of graphs in a single window. Because when you go for some research paper, if you want to pack your figures in such a way, it is compact, so you can give subplot and plot it. Okay, right. Now another important thing which I want to tell you is, quite often we are going to use mesh grid. Okay, so you might think, what is that mesh grid? Because we are going to discuss about the surface or a plane. I'm going to create a plane. So how the mesh grid is going to work? Okay, so the mesh grid means I'm going to get a grid like this, something like this. Okay, lot of meshes will be there, something like this. On how it is possible? By using the points here. Okay, so it returns a through 2D grid coordinate based on the coordinates contained in the vectors x and y. Okay, now x is a matrix where each row is a copy of x. So each row will be a copy of x, and y is a matrix where each column is a copy of y. I will show you. I have taken a small example. Then the final answer will have length of y rows, length of x columns. Okay, because when you want to create a plane or a surface, I will be using the mesh grid. Okay, so now let me see how it works there. Okay, see, I'm having the same thing. So first my thing is x is 1 to 3, y is 1 to 5. I'm going to create a mesh grid for this xy points. Now let me run this and I will show you the answer. Okay, a small thing. See, so now what is that x? X is 1 to 3. Okay, so it contains how many? 1 2 3 1 2 3 1 2 3 5, because it's based on the y's dimension. 1 2 3 1 2 3 1 2 3 1 2 3 5 times. Now this is y is based on the elements of y with dimension of x. So dimension of x was 3. So 1, 2, 3, 4, 5. One first column, 1, 2, 3, 4, 5. Second column, 1, 2, 3, 4, 5. The third column. Are you clear? Because x is 1, 2, 3, but y dimension is 1 to 5. So 5 rows has to be created with the value 1, 2, 3, 1, 2, 3, 1, 2, 3. Simply when you come to y, okay, y values are 1 to 5. How many elements was there in x? 3. So 3 columns has to be created with 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So now the final xy will be like this. I think I have suppressed that one. Okay, see 1, 2, 3, 1, 2, 3, 4, 5. So you will be having x like this and y like this. Okay. Now for each x and each y, I can plot those points. That will be in a form of a grid, mesh grid. Okay, it will be in the form of a mesh grid. Okay, why I'm telling this is because I am going to use this mesh grid later, so you should not have a confusion in this. Okay, so how it is being done? X is 1, 2, 3, y is 1, 2, 3, 4, 5. So I'm creating this x. Okay, so the dimension of x is defined by the element in y. So it should have 5 rows with 1, 2, 3, 1, 2, 3, 1, 2, 3. Now coming to y, the y is element is 1, 2, 3, 4. The dimension decided by x. X dimension is 3, so it should have 3 columns. Okay. Now you can see both are same. Now easily I can use that and I can pair it and I can form a mesh grid. Okay, mesh grid. That's a very important idea which we'll be using later. Okay. Now going back to this. Now, okay. Now with this little bit introduction to MATLAB, I think MATLAB is a big ocean. But what I've tried is these are some prerequisites which we need to understand the further slides. So then using this idea, now let us move to the next one, calculus. Okay, so our theme of today's webinar is how to visualize or how to understand calculus better using MATLAB. Okay, so according to Richard Courant, calculus is the outcome of a dramatic intellectual struggle which has lasted for 2500 years. Okay, so the invention of calculus paved way to many applications. Okay, now gradually I'll move to single variable calculus. So what you will do, you first you will be defining a function. Okay, once you define the function, you will be trying to find its limit. Okay, the limiting, that limit leads to another idea known as continuity. Then that leads to idea known as derivative. Then we will be seeing its applications in maxima, minima. Okay, whenever you're having a function, we'll try to optimize the function. For example, I'm having a profit in form of a function in a given domain. I'll be trying to find its maxima, minima. Okay, so everything goes like this. First function is defined, then limit of a function at a particular point is defined, then there comes the continuity which pave way for the derivative, then we are moving into its applications. Okay, so I'm not going to ponder more on this because you people know this idea, but to just make a quick recall, the function f is a rule of correspondence that associates with each object x in one set called the domain and a single value f of x from the second set, and the second set is known as the range. Okay, so usually what we will do when no domain is specified, we will be going for the natural domain, which is the largest set of real numbers. Okay, but usually the domain, when you choose a domain, you should be careful. You should be careful that division by 0 you have to avoid, and you have to avoid square root of a negative numbers. That means in a layman's sense, I can say those points which cause a singularity, I'm going to remove it. Okay, I'm going to remove it from my domain. Okay, now with this idea, now let us move to the limits. What is limit? Limiting is an approaching idea, is it? So I can say as limit approaches C, this f of x is near L. Okay, that means when x is near but different from C, then f of x also is near to L. And we know in a single variable calculus, it is very similar to standing on a railway track. Okay, suppose my railway, I am the point where I'm I'm going to approach me from two different sides. Either it can happen from right or from left. Okay, I'm starting a railway track. So what is the thing of hitting a train hitting me either from right or left? Okay, if these two limits are same, then I can say that is my limit L. Okay, and the next meaning is the precise meaning, the meaning which mathematician prefer. It's because I want to give a mathematical meaning for it. So given epsilon greater than 0, okay, there is a corresponding delta such that the length f of x minus L is very less than epsilon, provided the distance between x and c is also less than delta. You know this idea. Okay, now we will extend this idea to continuity. So what is limit? Limit is an approaching case. As x approaches x, your f of x also approaches a particular value L. Okay, now we will visualize this in MATLAB. Now let me move one step further. Once I talk about limit, next my idea is continuity. So what is continuity? That missing piece, x approaches a particular thing from right, from left. At that point, what happens? So if I'm able to fix the missing piece, that is my continuity. Okay, so I'm going to find what is the value of f of x at c. Okay, if my right hand limit and my left hand limit and my value of the function are that is same, then I can say it is continuous. Okay, it is continuous. Now we have seen some idea what is a function, how the domain plays a very important role in defining a function, and we have seen what is limit. Okay, and we have seen what is continuity. Okay, that missing piece, fixing the missing piece is continuity. Okay, so now let us view everything in MATLAB. Okay, now let me go back to this arm. Okay, so now let me run this problem. This program, I will run through this code. I'm going to plot the function 1 by x minus 3. Okay, so what I should avoid? I should avoid x equal to 3, because at x equal to 3 a singularity arises. So apart from that, if I try to plot it, I can plot my graph. Okay, so I have used fplot. It's a function plot. I'm going to plot the function f in the domain 2 to 4 with red color and so on. All these things are added to enhance the figure. Okay, so fplot means you're going to plot the function. What is a function? Function of defined there as 1 by x minus 3. So remember, most of the codes here are designed by our team of faculty members in Chennai. They have done they did all the codes. I'm using those codes, and I have just modified some codes. Okay, so here what happens is I'm trying to plot this f for a given function. So this code is not a generic code. It is a specific code for a specific function. Okay, remember, it is not a generic code. Generic code is going to come later. Okay, so generalized code is going to come later. Now let me run this. Please, at any point of time, if you're having doubt, you can stop me and ask. If I know that, I will give you the answer. Okay, so see, clearly this tells this is not equal to 3. At 3 it is not defined. Excuse me, just wait. Someone is knocking the door. I will just ma'am.
Sir? Somebody is presenting.
Sorry ma'am. Ma'am, can I continue?
Yes, sir, யாரோ present பண்றாங்க ரம்யான்னு சொல்லிட்டு.
Please don't present. Ma'am, can you see my screen now?
Students, please don't present your screen.
Ma'am, can you see my screen now?
Yes, sir. Now it's visible.
Okay, ma'am. So this clearly tells me that the function which I'm talking about, it is asymptotically it grows. Okay, it doesn't touch the tree. It asymptotically grows. So this is I've taken this example to show that how the domain plays an important part. Okay, now let me take another example where I'm having a square root at the denominator. So square root means actually when I substitute the points, it is going to become 0. So singularity happens there. So let me run this. The same function, I'm defining a function 1 by square root of 9 minus x square. Okay, I am taking a open interval -3 to 3, because if I take a closed interval at -3 and +3, the function is not defined. That means a singularity happens there. So this is the corresponding bathtub function, where you can clearly see it doesn't touch 3 and -3, and it goes on asymptotically, it grows. Okay, so this is why I want to stress is choosing the domain for a problem is a very important thing. Okay, so now let us move to the limit idea. We have discussed what is the limit. Okay, here I'm going to run some problem where there is no limit, where there is a limit, and then continuity. Okay, now let me run the first code. Here I've given function as 1 by 1 plus e power 1 by x. Okay, I'm finding the left limit. LL means I'm finding left limit, that is limit f x at, okay, I want to find at 0 0, so 0 left. That means I'm going to approach 0 from left and from right, and I'm also finding the limit. This is the left limit, right limit. If all the three are same, then I can say limit exists. Okay, then this I'm trying to plot this in this range. Okay, I'm going to plot the function which I'm talking about. Okay, and I'm also going to plot the function. Okay, and where it finds. So suppose I'm finding the limit from left side, I will get a value. I'm also going to plot that. From right, I'm going to get a value. I'm also going to plot that, and I'm going to also plot the L. Okay, now let me run this. I am not going into the codes because our idea is understanding calculus using this MATLAB. So you can ponder upon the code later. You can get the code from map. See, if let me go to the value first, the command window. I can see when I approach this function, okay, from left side, it value is 1. From right side, value is 0. So L, whether the limit exists? No. NA means it is not a number, so limit does not exist, which clearly tells me, see, as I approach from right and from a left, I can see there is the different values are the values are different. Limiting values are different, which clearly shows from this figure this particular function as it approaches 0 doesn't have a limit. Okay, because left hand side value is 0, right hand side value is different. Okay, so sorry, left is 0, right is 1. Clearly tells me that is the function which I've taken into consideration doesn't have a limit. Okay, now let us see the another problem here. The thing I've taken a function x square minus 3x by x square minus 9. Okay, I'm trying to find what happens as x tends to 3. Okay, I'm trying to find the limit. What happens to the limit as x approaches 3? So I'm finding the left limit. I'm finding the right limit. LR means limit at the right, limit from right, limit from left, and I'm finding the limit. And I'm trying to plot this in a given domain. Okay, that. Let me run this. Let me go to the first command window. See, my left limit, this is the given function. My left limit is 1 by 2. My right limit also 1 by 2, and limit value is 1 by 2. So here, this figure clearly shows that as I approach from left, as I approach from right at the function, see, this is 3. When I approach from right to that particular value x equal to 3, from left to that value, there is a limit. Okay, you can clearly see, no? So when I approach here, both is going towards a same value. So I can say limit exists for this particular function as x approaches 3. Okay, which is clearly mentioned in this code. Everything I have written here. Okay, R. Okay, you can see O means you will get a puncture hole like this. Okay, you get a puncture hole like this. This clearly shows the left limit is there, the right limit is there, and the values are same. So limit exists for this particular case. Okay, now what is the next idea? Now I'm trying to show that the continuity. The same problem, if I try to fill that hole inside, it becomes continuous. Is it? So now let me go to the continuity. So here I have taken the problem that is f equal to x square minus x by x square minus 1 for x not equal to 1, and x equal to 1 for x, and the function value is 1 when x equal to 1. you can see f of x equal to, I can write as x square minus x by x square minus 1 for x not equal to 1, and x equal to 1 for x equal to 1. Okay, so that is my corresponding f. So I can use piecewise because I'm having two different areas there for x equal to 1 and x not equal to 1. So I can use piecewise, and I can mention like this here. Then I can find what happens to the function as it approaches 1 from left, it approaches 1 from right. Okay, and I'm finding the limit of that function, and all these are to visualize how it goes, to visualize my given function, my where is my limit, all these things. Okay, now let me run this. Okay, if I see the command window, I can see 1 by 2, 1 by 2, 1 by 2. So limit exists. Okay, see, limit is there, but is it continuous? No, because there is a missing piece here. If I find the function value at that point, it is somewhere here. If this function value is also on this missing piece, then I can say it is continuous. Whereas in this case, it is, the limit exists, but it is not continuous. Why? Because the function value should be equal to this here. Is it? So the function, if this blue dot is on this white dot, means then I can say it is continuous. So this is a classical example of where the limit exists, but it is not continuous. Why? Because the function value is not equal to the limiting value. Okay. Now let me, another example I'm having where I can show you that. Okay. So here I've taken a function x square minus 4 by x minus 2, x not equal to 2, and x equal to 4 when x equal to 2. Sorry, f of x equal to 4 when x equal to 2. So I've chosen a function x square minus 4 by x minus 2 when x not equal to 2, and 4 when x equal to 2. Okay. Now same way I'm trying to find what is the left limit. Okay, the command is limit. If you give limit, it automatically finds the limit. To be more specific, I'm finding left right separately. Okay, left limit, right limit. Okay, then I'm finding the limit value, and I'm plotting all those values. Okay, I'm plotting the function, I'm trying to plot the points of my interest, all this. Okay, now let me run this one and show you. Okay, if I, let me go to the thing, see, my limiting value is same. Okay, they are all 4, and if you see now my function value is also equal to that limiting value. Okay, so which clearly shows that the function is continuous in the given domain. Okay, previous problem, this there was a hole inside this. Now I can see I am having a continuous thing, so which clearly tells that the particular function is continuous in this given domain. Okay, are you clear with this idea? Okay, so previously we saw it limit exists, but I had a punctured hole in, because limit is always a approaching concept, not equal to concept. When the value is equal to limiting value, then I can see it as a entire stretch without any break, so it becomes continuous. Okay, so with this idea, now we'll move to derivative and tangent line. So before that, because now we have defined the continuity, next thing we will be moving to the derivative. Okay, so derivative and tangent line, you people know this, but let me make a quick recall. What is derivative? Okay, so suppose I am having a curve as it is there in the figure, and the point is C. So this is C and this is C plus H. So this point, the point P is nothing but C comma f of C. F of C is a function value, and I'm having a C with increment of H, it has moved to C plus H. So the corresponding value Q is C plus H comma f of C plus H. So now this line is the secant line joining this P and Q. If I move along this curve, the secant line also moves, and finally it comes here, is it? So when it reaches here, it will become your tangent line. That is, let me first write what is the slope of the secant line. I know the slope is f of C plus H minus f of C by this H. As this H becomes smaller and smaller, or it approaches 0, what happens? That will become your slope, or f dash of C. We call that as f dash of C, or slope of the tangent line. Okay, so tangent line is nothing but the limiting position of your secant line. You just think you just moving this point. As this point approaches here, you can see this secant line will become a tangent line. So that is where f dash of c is limit as h tends to 0, as h approaches 0, f of c plus h minus f of c by h. Okay, provided that this limit exists and it's not equal to infinity or minus infinity. You know this idea before. Now, how to find the derivative in tangent line using MATLAB? So how to visualize this? Okay, so now let me the next one is okay. So, and I will also discuss about the applications of differentiation, and I will move. So once the derivative is given, tangent line is given, then we will be talking about the applications of differentiation. That is our ultimate aim. Our aim is to apply this for a given function and try to optimize the function, whether it is minimize or maximize. I'm going to use it to optimize. So I'm having a profit function, I'm having a cost function. So I want to optimize this. It means wherever I'm going to maximize, and I'm going to find the minimum value. So when you talk about this optimization here I can see it as the two things. One, in the closed interval. The closed interval means I'll be talking that is the absolute maxima minima. Okay, absolute maxima minima, or in a particular neighborhood, it is called as local maxima or minima. Okay, local maxima, that means in the open interval, local maxima or minima. Okay, this is very similar to I can easily a best analogy is, suppose in my class, in a particular bench, I can find who is the student who is taller and who is smaller, or in the entire class I can take a person who is taller and smaller. Okay, those are absolute maxima minima. When I go for a particular bench, I can think of a local maxima minima. Okay, so here the 3 points are very, very important. One is end point, because your extreme value can happen at the end points. It can happen at stationary points. That means we usually call this as the point where your f dash becomes 0, or the points where the f dash is not defined. Okay, those are called singular points. See here in this graph, you can see there's a sharp edge. Sharp edge means the derivative does not exist. You know that, sharp edge. That's why in mod x, even though it is continuous at x equal to 0, okay, but it is not derivable at x is 0 because it has a sharp edge. So see, there's a sharp edge, and here you can see you'll be having a vertical tangent. Okay, so all these are called the singular points. Okay, and you can see there is a jump here, and then the curve goes. So you should always take care your endpoints, then your points where f dash of c is 0, and points where f dash is not defined. Okay, so all these are candidates for your stationary for maxima minima. Okay, so now with this idea, now let me go to that one. Okay, so now I'm going to derive, I'm going to go for derivative and tangent line. So here I can find derivative in two ways. I can directly apply the formula which we discussed. Is it limit as a limiting case, as h tends to 0. Okay, in that way also I can define, or MATLAB gives you a simple way of doing it. If you give diff, first you define the function f, then you give diff. F means by default it will do the derivative with respect to x. Okay, so here to start with, I'm just using the definition as such. So m equal to limit f of x minus f of 2. What is f of 2? That's nothing but your function value, is it? Because at the point 2, 1 by 2, I'm going to find the tangent line. So f of x minus f of 2 by x minus 2 as x goes to 2. Okay, that means here I'm doing as this, finding the limit when x is 2, and this gives me the tangent line. We know it is y minus y1 equal to m into x minus x1. So I'm bringing y1 this side, that is nothing but the function value f of 2, and I'm putting in a thing called tangent line, and I'm going to visualize that. Okay, Okay, all these parts are for visualization. Don't worry, even though if you don't understand right now, it is a very simple one. You can keep the code with you and you can explore on that. Okay, because I'm telling that this seminar webinar is for not on for MATLAB, how to understand calculus using MATLAB. So I'm going to use MATLAB as a tool to understand my calculus. Okay, now let me run this one. I'm going to run this one and let me see. Okay, my tangent line is 1 minus x by 4. Okay, that's my tangent line. See, this is the curve. I have plotted the curve. Okay, the given f, it's 1 by x. I have plotted this, and this is the tangent line at the point 2 comma 1 by 2. So this this tells us how the tangent line is going to work. This is the curve and this is a tangent line. So if you show this to the student, they will easily understand, oh, this is the tangent line, how it works. Okay, so now this next idea is if I'm fast, please let me know, because I'm having some 25 programs. I have to discuss all this. Derivative as a function. So here what we did, I used the idea of limit to find the derivative. Here m equal to idea of limit to find the derivative as x as here h is 2. Okay, but here what I'm trying to do, I'm going to use the built-in function, which is quite simple. So now I'm going to find the derivative as a function. So this is my function x power 4 plus 2 star x. Df is differentiation of f, that is diff of f. If you give diff of f, it finds you the differentiation of this f. If you didn't mention anything, it implies your default will do with x. You might ask what to do for a function of more than one variable. There you have to specify with which variable you are going to differentiate. Okay, right here diff of f, and I'm going to substitute the point, and I want to find the derivative at x equal to 2. So subs, I'm using a new function known as subs df at x equal to 2, and I'm going to plot this function. Okay, now let me see run this. The code already I've shared with ma'am. You can get it later and you can work and see. You no need to install MATLAB in your system. As I mentioned, use the cloud platform. Okay, so this is my given function. Okay, x power 4 function. Then I'm differentiating it. It becomes an x cube function, which is given like this. So why I using this program is to find differentiation. There's a simple command is available known as diff. Use that, you can easily differentiate. Okay, all the other things are for you to plot in a given domain. That's it. Okay, in a given domain. Now let us go to the application of differentiation. As I mentioned, maxima minima. Okay, I am trying to find the absolute maximum minima for this particular problem. That is f of x equal to 2x cube plus 3x square. Okay, and on the interval minus 1 by 2 and 2. Okay, so my domain is restricted to minus 1 by 2 and 2. It is a closed interval. Okay, so now first I am getting the function here, then I need to differentiate that function. Is it? Then what you will do, you will solve that function. Is it? You will be putting dy by dx equal to 0. So that is done in MATLAB using a simple command known as solve. If you give solve this with respect to x, it solves the equation and it's stored in C. Okay, so now your values, critical values, are stored in C. Okay, now you clearly know that if you solve this, if you put for this particular case, if you put df equal to 0, you will get 0 and 1. But what are the possible points for maximum minima here? Boundary points is also included. So minus 0.5, 0, 1 and 2. So there are 4 points. You have to discuss what happens to this function at these 4 points. Then only you can select one which is going to be the maximum, which is going to be the minimum. Because I have taken a closed interval. Closed interval endpoints also plays an important part in deciding your maxima minima. So I'm defining my P like that. minus 0.5 is 1 by 2, 0, 1 or the value which I'm getting here, and 2 is the my right side boundary. Okay, so at this point I'm finding the function value. See, because I have to find the function value, then only I can tell which is maximum minima. I'm finding the function value. Okay, and it clearly tells me, okay, that absolute maxima will be f, it happens at f of minus 1 equal to 1 and f of 1 equal to 1, and absolute minima happens at minus 4. Okay, and these things are for plotting that one. Okay, now let me run this. I'm going to run this one. I'm not going to get anything from the keyboard because I have directly given the function here. See, this is clearly, since boundary is also there because it's a closed one, I can clearly see. So this, so my absolute maxima at it happens at two places. One is minus 1 by 2. Okay, when x is minus 1 by 2, this one, see, x is minus 1 by 2, this one value is 1, and it happens at x equal to 1, the value is 1. So these are the two absolute maxima happens at these two cases. Okay, and absolute minima is I'm having one minima at 0, 0, and another one is minus 4. So this is my absolute minima. So that is one absolute minima and two absolute maxima, because both this value have the same function value. Okay, so which clearly tells us that in a given closed domain, okay, I can find the maximum minima of a given function. That function can be any function which in real life we come across, a profit function, okay, or the cost function, or whatever it is. Okay, right. Ma'am, any doubts from the student side, ma'am? In
Participants, any doubt?
so far, any doubt?
Participants, if you have any doubt, you can clarify now.
Okay, ma'am. We'll see the last, ma'am. Well, if I try to finish it off. Okay. Okay, ma'am.
Okay, sir.
Okay, we'll continue.
Okay, sir.
Now I'm going to find the local extremum values. Okay, local extremum values. So the same thing here. I can clearly see the critical points are those where your f dash is 0. When you put f dash is 0, you'll be getting some values, and where f dash is not defined, the same thing I'm doing it for a local maxima minima. I just will wait. See here, my boundary points are not, because this is an open interval. I'm talking about open interval. So this is my local maxima, and this is going to be my local minima. The same idea. You find the critical values. You solve those values that are going to be critical value. But make sure whether f dash is undefined at some point inside your closed interval. That will also will be a candidate for your optimum value. Okay. So this is with respect to the open interval thing. Okay, next we will move to integrals. Okay, integrals first we'll deal with definite integrals. Okay, for definite integrals, obviously we'll be adding that limits. So here let me talk about the indefinite integral. Okay, let me skip these two 14 and 15 because those are a general one. Now let me go to a important one, because we know integration is nothing but it's based on Riemann sum. Okay, so here in MATLAB a separate command is there known as R sums. Okay, a command is known as R sum. Okay, so using that I am going to find the integral 0 to 1 x square dx. Okay, I'm going to find integral 0 to 1 x square dx. So what will be the value? You know, it is x cubed by 3. Okay, so it is 1 by 3. It is 0.3333. Is it right? Now let us try to find the integral using Riemann sum. Riemann, repeatedly you are going to find the area. Is it? Then that means when delta x into your f, you'll be multiplying that. Then you'll add all the strips which gives you the final answer. Okay, that is the Riemann sum. Now let me run this one, the Riemann sum. If I run this, since I used R sums, okay, that particular thing will open a interactive window. This is an interactive window which starts from 2 strips to 128 strips. See, 128 strips. It will be 2 strips to 128 strips you can do. Now what happens, you can show the students when the strip is 2, I should get 0.333, but the value is not a refined one. What is the idea here? Increasing more number of strips, more accurate will be an answer. See, I'm increasing the strip, the value is getting refined. Okay, see, it is getting refined further. Okay, so in such a way, an interactive fsum, the fsum is an interactive command which tells us how the answer is getting refined as we increase the number of strips. Okay, are clear? So this will be very useful for students to easily understand the idea of increasing the number of strips, more accurate will be an answer. Okay, so this is Riemann sum, which I want to show you especially because you will get an interactive window which you can scroll to the right or left and see how the value is going to change. Okay, and now the another thing, the area between two curves, right now I will skip this. Okay, I will move into the multivariable calculus. Okay, multivariable. So now we are moving into the next dimension, multivariable calculus. Now let me recall what we have seen so far. We just brushed the some basic ideas in MATLAB. Okay, and we defined, we discussed what is a function, what is a limit, how to visualize it. Okay, then we discussed about the continuity and how it looks in when you code in MATLAB. Okay, and what is how to find the derivative. Okay, and how to visualize a maxima minima. Suppose you are given a function, how to find or how to visualize its optimum values. Now let us move to the multivariable calculus. Okay, now I will also skip all this thing because I'm multivariable calculus. Okay, so the same thing is, I am going to talk about a function of more than one variable, that is f of x comma y. What is f of x comma y? Is nothing but a surface. I'm going to talk about a surface. Okay, a surface f of x comma y. That means z equal to f of x comma y. Okay, remember that here finding the limit is a very big challenge, because in single variable calculus you can approach from right, you can approach from left. Okay, and if both are same, that is the limit. But in the case of multivariable calculus, the challenge is, suppose assume I'm standing in a space. Okay, I'm just floating in air from the ground. Okay, in how many ways a ball can hit me, how many paths a ball can hit me? There are infinite number of paths. So it is not possible to go and check whether the limit is same in all the paths. So the challenge is, it is very, very difficult, because I cannot go and check all the paths individually. Okay, so better I have to rely on the mathematical definition, which it is, for given epsilon greater than 0, there is a delta such that your f of xy minus a less than epsilon whenever the distance between xy and a point AB are less than delta. Okay, so this thing can be further easily, suppose finding the limit for a function of more than one variable is a challenging task. Okay, but there are simpler ways of doing it. Okay, you can think of Squeeze theorem. Okay, suppose you're having two functions, and the function of my interest, which I want to find the limit, lies inside that. And if I have the limit of the two functions on the right and left, then I can say that will be my the limit of the function of my interest is the same, because that is called Squeeze theorem. I'm going to squeeze my function inside two functions, and I'm going to find the limit. So all those things are there. So finding limit is a Herculean task in multivariable calculus. So once you find the limit, then the continuity idea is very same, which I've already seen. If the function value is equal to the limiting value, then you can say it is continuous. Okay, now, so the main thing of studying a surface is we are going to find the limit, okay, as xy approaches a particular point or 0 0 or any point AB. Once it has been done, then you will be going for continuity. So that means the function value should also be same as the limiting value, okay. Then once before going into the derivative, let us discuss what is level curves and contour plots. Very important idea, which is going to lead us for the maxima minima, okay. Suppose let us assume I am having a hill is there, I am standing here, okay. So I am just going around the hill at the same height from the ground. My friend is standing somewhere here, he is also going around the hill at the same height. Similarly, another person is going around, okay. If I press from the top, let me assume that I'm going to press the hill from the top, I can see plot like this, okay. So these are called contour plots, okay. So this contour plots plays a very important role, okay, for finding the optimality of a given function, okay. So now this contour, these are called level curves. These are called level curves. I can say this height is, for example, some 10 feet, means I can say f of x comma y equal to some 10. 10. Next is f of xy is some 12. So I can create lot of plots like this. So that is my contour plots, and these are called my level curves, okay. So the best way to study your surface is using this level curves. We will be using this idea of level curves when once I reach the Lagrange multiplier, okay, Lagrange multiplier idea. Okay, now once a surface is defined in a particular domain, we are going to check whether the limit at a particular value exists, and we're talking about the continuity. Next comes the partial derivative, okay. Partial derivative, you all know partial derivative is, suppose I'm finding dou f by dou x, okay. Y is going to become constant, that means I'm moving along only x, okay. Similarly, dou f by dou y means x is constant, you're moving along y. Now how to visualize this, how the students will understand this? Just to say that it is moving along x y means how they're going to understand. You just think of I'm having a potato, okay. Potato is like this, I'm going to cut that with a knife, okay. So suppose knife is like this here, I'm having a potato something like this here, okay. So this thing I can plot a curve where the knife cuts the potato, okay. So suppose at this point if I draw a tangent, okay, that will be my partial derivative with respect to either x or y depending on the situation at that point. Suppose this is x and y axis, okay, x and y axis, I'm having a surface here, I'm using a constant plane x equal, I'm cutting like this, my knife is like this means, so this is constant, it is going to vary along x, so I'll be finding dou f by dou y. Similarly, if I cut like this, okay, what happens, this is going to remain constant, this plane is going to remain constant, so I'm going to find dou f by dou x, okay. So at this particular point I can draw, so I can find what is dou f dou x at that point. At this point I can draw one tangent, I can find dou f dou x at that point. So this is the idea of partial derivative, okay. So you can think of a surface, you cut with a knife, so you can trace a curve where the knife and the potato is there, where it has cut the potato, you can draw a line, and you can at any point of your interest you can draw a tangent, that is going to be a partial derivative, okay. So now let us try to view this, see, so something like this, okay. So here you can see your plane, this plane is a constant plane with respect to y, so y equal to some y naught, okay. So at this point you can find what happens to dou f by dou x. Similarly, at this point you can find what happens dou f by dou x at this point. So now we will try to visualize this using MATLAB, okay. So that is an important thing, okay. You can easily see, okay. See, I'm having a code like this, I'm going to find the partial derivative of f of xy is 4 minus x square minus 2 star y square with respect to x and y at the point 1 1 and I'm going to visualize it. I'm going to find the partial derivative with respect to x and y at the point 1, 1, and I'm going to visualize it. So here it is a more specific code. Sorry, it's a more general code. I can give any function for that matter. I'm going to give this function. The code is designed in such a way you can give any function inside. Okay. So first I'm going to input the function of the function which I'm going to find the derivative. Then enter x value at which derivative. So at the point I need 1, 1, no 1, 1, 2, 1 at the point of my interest. I'm giving as x1, y1. Then I'm going to find z1 because I need the height. Okay, because it's on the surface. So subs. So in z, okay, in this function, first I'm replacing x by x1. So now the function will be in terms of only x, will be in terms of x1. Then y I'm going to replace by y1. That means I'm replacing in z. I'm replacing wherever there is x by x1, y by y1. Okay, and I'm going to visualize this. It is given by Ez surf. Here I'm going to visualize the surface. I'm giving Ez surf. Okay, and then I've given some two options. That is, if you want partial derivative with respect to x, you give 1. If you want partial derivative with respect to y, you give 2. Okay, so if you give 1, what implies you want partial derivative with respect to x, so it goes into this block. Okay, see, it finds what is the derivative of f diff of z comma x, that means with respect to x. Okay, then I'm going to find the slope, means I'm going to substitute the value of x and y1 because at that point I need. Then see, I'm creating a mesh grid because I want to view that plane which cuts the surface. I want to view the plane which cuts the surface, and I want to draw the tangent at that point. Okay, now let me run this one. So this is the general idea which I'm telling here. Okay, please go through the code. Okay, general idea is I'm going to find the surface. First I'm going to plot the surface, then I'm going to plot the plane which is going to cut. Whether it is dou f by dou x means I'll be having a constant y plane. If it is dou f by dou y means I'll be having a constant x plane. Then at my point of interest I'm going to draw a tangent that is going to be my partial derivative at that particular point. Okay, so now let me run this one. I have to give the from the keyboard because I have to key in the thing. It is 4 minus. Let me copy this directly here, and let me go here. Let me run this again. Let me close this. Okay, so let me give this function. It's 4 minus x square minus 2 star y square. This is my function. 4 minus x square minus 2y square. Okay, right. At what value I need? I need at the point 1, 1. So I'm going to give x1, enter the x value at which derivative has to be evaluated. 1, y value 1. So z value is 1. Okay. Then it asks me whether, so first what happens? The surface is plotted now. The surface is plotted, which is a function of xy. Okay, this is surface. Now it asks me whether I want to go for dou f by dou x or dou f by dou y. Now let me give dou f by dou x 1. Let me give 1. Okay, so it finds the dou f by dou x. It finds a slope. Okay, now let me give the range as a vector 0. Let me give 0, 5. The range where I want to plot it. All these things you can forget about. See, this is the surface. This is the plane which I'm talking about. Remember, I'm finding dou f by dou x. So I'm having a constant y plane which cuts the surface. And you can, if I move this one. See, you can see the tangent now. At this point, I think if I'm, since it is cloud, the only issue is it's based on your internet speed also. Okay, so at this point of interest, I am drawing a tangent at that point. So this gives me the partial derivative. See, so this is my potato surface. this is my knife means this place I can find a curve. I can find a curve at that point. At a given point I can draw a tangent. That is your partial derivative at that point. Okay, now the same thing, let me do it for dou f by dou y. Okay, I'll do it for dou f by dou y. Now let me this, and you can see Z3, so many things are coming here, and not to avoid that, let me give semicolon. If I give semicolon, it will suppress it will suppress the output. You won't get the output in the command window. Okay, I'm going to suppress everything. Okay, I'm giving semicolon. Let me run this. Okay, the same function which I want to discuss later. I'll be having it in here. This is the function, and 1, 1. Okay, and vector let me give 0, 5, because in that domain I'm going to view that. Oh, sorry, I've given 1. Excuse, sorry, just wait. I just mixed up with. Okay, right, let me I have to give 2 no, because I'm going to visualize the next one. Enter the function. This is my function 1, 1. It asks, I'm giving 2. Okay, and let me give the same vector 0 to 5. This is the range in which I want to figure out this Z range. Okay, right. Okay, see, now the constant plane is your x plane. Okay, your x plane, this is a surface. So if I move along this, y is going to vary. So at a particular point, see, I've drawn a green color line. That is a tangent line. Green color line, tangent line. I think you can view this line. Okay, I just tilted it, I think. Let me run this again. Okay, I'll show you. Just run it again and I'll show you. Then I will move to the next one. So the beauty is I don't have the software in my laptop, but I'm using the cloud. Okay, so that is the beauty of using cloud platforms. It is also available for R, as Sar said last class, Sage. Okay, Octave. Okay, as of my knowledge, it is available for these things. Python. Okay, it's still available for all these things. Let me give it as a vector. Okay, so you can see this green color line. That is the tangent at the point 1, 1. At the point 1, 1, I draw a tangent line that gives you the partial derivative at that particular point. Okay, so partial derivative is nothing but you're taking a surface, or let us assume you're having a chamina. Okay, I'm going to cut the chamina from x-axis or y-axis, and at a particular point I'm going to draw a tangent. Okay, so this is my partial derivative. So far any doubts? So far any doubt? Rang, any doubt in this? Is there any doubt? Okay, now let me move to the directional derivatives. Okay, so directional derivatives. So in what way it is different from the partial derivative is, now partial derivative means I'm moving along x-axis, y-axis. I'm going to find what is the difference that happens. Okay, the rate of change that happens with respect to x and y. In the study of fluids and this current, okay, the flow is not in any particular x or y direction. It is isotropic. That means it can move in any 360 degree. Suppose a fluid is moving, means I'm taking a particular particle, it will always not move in x and y axis. It will move randomly in some direction. So I have to mention along what direction, means I have to tell what is the along which vector my fluid particle is moving. Okay, so here rather than talking about on x and y axis, I'm talking about arbitrary direction. So I should mention along which vector it is going. I want to find its derivative. Okay, I want to find the derivative along a given vector. Okay, so what at a particular point, the same idea, at a particular point along a given vector. So what I have to do, I have to rely on the gradient. I have to rely on the gradient function. Okay, I have to find del f. You know what is the gradient? It is dou f by dou x I vector plus dou f by dou y j vector. Okay, so that del f in dot u here means u cap. So along any vector is given, you want to find the unit vector, so you will normalize the vector to get the unit vector. Okay, how to normalize the vector? Vector by its modulus gives you the normalized vector, otherwise known as unit normal vector. Okay, so that is your directional derivative. Now let us visualize that directional derivative. Okay, so here I have taken one example where my surface is 9x square 9x square sorry 9 minus x square minus y square. Since I have created points for x and y, I said I have to use x dot cap 2 minus y dot cap 2y, because I'm having many points for x, many points for y. I have to use that, so I have to use x dot and y dot. That means element wise I'm going to operate. Okay, then I'm plotting the surface. Okay, and I'm using this view means to rotate, because for the problem which I'm going to discuss, the vector, the tangent will be that side. So I'm going to rotate that so that we can view from this side. Okay, then I'm going to find, that is as we know that, okay, I'm after finding the my idea is to find the directional derivative at a point p11 along a vector I vector plus j vector, that means 1 1. So if I try to find unit vector, it will be v vector, that means the vector I'm talking about 1 1 I plus j by its modulus. So I'll be getting 1 by root 2 1 by root 2. Is it 1 by root 2 1 by root 2? So now I'm choosing any point xy on that line which passes through 1 1. So it can be given in parametric form. That is nothing but it is given by that p point px vector. That means the px vector means, you know, ox vector minus op vector, that will give px vector minus t times your unit vector. So you will be getting two equations in parametric form, that is x equal to 1 plus t by root 2 and y equal to 1 plus t by root 2. X equal to 1 plus t by root 2, y equal to 1 plus t by root 2. Okay, that means this is the point xy point which is on the line in parametric form. Okay, now I have taken my domain to be minus 2 and plus 2. So for your 1 plus t by root 2 lies between minus 2 and plus 2. That means your t lies between minus 3 root 2. See, the value is here, minus 3 root 2 to plus root 2. So I'm creating I'm creating points between minus 3 root 2 and plus root 2. And I can see these are my parametric equation of x and y. 1 plus t by root 2, y equal to 1 plus t by root 2. Okay, now I am plotting this line with this parametric form x and y, because I am having points for t which has been generated here. Using that I am having x and y, so I can plot the line. Now I am plotting the surface. I'm plotting the surface. Okay, so plotting the surface means directly I can give x is there, y is there, z is there, I can plot it. Okay, now I want to find the tangent line. So for tangent line I need the derivative dz by dt, dz by dt. But clearly I know that f x and y are function, z is a function of xy, because that is the surface. Z is a function of xy, but x and y are functions of t. So I have to find dz by dt equal to dou f by dou x into dx by dt plus dou y by dou y into dy by dt. Is it? Because x is a function of t, but f is a function of xy. Okay, you know this the derivative. Okay, you might have studied in the total derivative. So if I apply this, dz by dt will be minus root 2. It will be minus 2 root 2. That means your, what it implies, minus 2 root 2. That means if you move 1 unit along the unit vector, there is a drop in z direction by minus 2 root 2 units. I will show you in the figure. If you move along the vector, for each and every unit of movement in the in the direction of unit vector, there is a drop in the minus 2 root 2 units in the z axis. Okay, once if you find this, then you can clearly see that the vector pointing in the direction of tangent line will be 1 by root 2 comma 1 by root 2. Those are two things which you obtained from the unit vector u vector, comma the third component will be your dz by dt, that is minus 2 root 2. So if you take that along with the vector lambda instead of lambda, then you will be getting this line 1 plus lambda by root 2, y equal to 1 plus lambda by root 2, and z is 7 minus lambda by root 2. You can easily find this because you are going to find the vector px vector equal to lambda w vector. If you find this, you can find. So now let me visualize this. I know definitely this concept you have to go through in detail, but since I'm running this code, I'm just giving the outline of what I have done. Okay, let me run this. Run this. See, so this is my surface. Usually what I did last day, I just cut this using either using a constant plane in x-axis or in y. But now I want to find what happens to the vector which is along 1 1. So this is 0 0 along 1 1. This is positive side. Okay, along 1 1. So assume it is moving like this. Okay. So what happens at the point of my interest? I'm going to at 1 1. I'm going to find the derivative, which clearly tells that the derivative is negative, is it? Because for each and every unit I walk along this vector, there is a minus 2 root 2 unit is coming down in z. Okay, in z direction it is coming down. Okay, so you can clearly see this is my directional derivative. This is my visualization of directional derivative. Okay, so previously my plane was like this. Now my plane is like, you can think of this plane. You are cutting this surface with the plane like this. With the plane like this, a plane similar to D, you're cutting this and you're finding the derivative at this point. You can see as you move along this, walk along this line from 1 1 0 0, if you walk along this, there is a decrease in the units in z. Z is coming down. Okay, so this way you can visualize your directional derivative, which is a very, very important idea in the study of fluids and currents. Okay, okay. So I hope you understood a little bit, because definitely I know that. Please get the code and you can go through it. Okay, right. Now let me go to the vector field, and I'll come back to this again. And similarly, I'm going to visualize the vector field. Okay, this vector idea, its eigenvalues. Okay, and eigenvalues plays a very, very important part in image processing, where you're compressing image or you're expanding an image. It is based only on this eigenvalues and eigenvectors. Okay, so here what I'm trying to do, we are trying to visualize how a vector field is. Usually they say in a vector field, but you know how it looks. Okay, now let us try to visualize a vector field. Okay, now I'm going to give this function. This is my vector. It is given as xi vector plus yj vector by square root of x square y square. I'm going to visualize this vector field. That means at each and every point in the domain, I'm going to draw a arrow. Okay, right. So now I'm going to input the vector in the form of xy. Okay, then since I'm giving this in terms of x and y, my aim is to find the point element wise, because I'm going to do the element wise, because I'm going to create some points for x. So what I'm doing vectorize. Vectorize is very similar in writing x dot. Your vectorize means it converts the function in such a way it is ready for element wise operation. So this given f, because now this f has two components, because I'm going to give ij, one is f of 1, so that I'm going to vectorize, and similarly f2, the j component, I'm going to vectorize. Then I'm going to fix points for x-axis. I'm creating points for x, and I'm creating a mesh grid. In that mesh grid, I'm going to view. But what is the command for drawing the arrow? It is QUR. It's QUR in MATLAB. QUIVER, QUR in MATLAB. Now let me run this one. Let me, I think, since I will give CLC and I'll do it again. Now let me go here once again. I will run this section alone. Okay. Okay, I have to enter the function. Okay, let me give the function here. Okay, so I'm going to give it as a vector form. So I'm going to bracket like this. Then my first component is x by square root of. Okay, so it is x divided by sqrt of x square plus y square. This is my first component. Okay, my second component is y by sqrt of square root of x square plus y square. Okay, right. This is my second component. Okay, I think I have given correctly. Okay, right. Okay, see, this is the mesh grid thing. See, this will be a corresponding vector field. It is a two-dimensional vector field. Okay, and each and every point vectors are drawn. I'm giving this. Suppose I'm giving xi plus yj, that is a vector field. If I give 2y plus 3j, it is a particular vector. Okay, so I'm just plotting only the vector field. So this is your vector field for a two-dimensional case. Now let us take it further to a 3D. In 3D case, the same thing. Let me the same idea, but one more element is added. Let it be r. R is added to it, and I mentioned no that what is vectorize does. Let me see how vectorize is. See, it becomes x dot, x dot, x dot. The same thing. If you give vectorize, it is very similar in writing x dot square. Okay, it automatically it vectorizes the given function. That means it is ready to accept input in element by element form. Okay, now let me run this vectors in 3D. Oh my god, let me give that CLC. Okay, right. Let me run this again. Okay, so my vector now is I want to think of three components should be there. I'm opening a bracket, square bracket. First component is x divided by sqrt of x square plus y square plus z square. This is my first component. My second component is y by the same thing. Let me copy this and paste instead of wasting time. Control-C. Then z. Okay, so given the three components x by plus y by z, right. See, so this is the corresponding vector field in 3 dimensions. Okay, corresponding vectors in 3 dimensions. Now you can give anything further and you can see how it behaves. Okay, so this is the corresponding vector field in 3 dimensions. Because this, if you this vectors, once you talk about vectors, then eigenvalue, its eigenvalue, everything, that is the base for image processing. Okay, if you want to compress, or if you know that linear algebra very well, okay, it is very much applied in the image processing area domain. Okay, right. Now I have vectors. Vectors is over. Then let me Lagrange multiplier I want to mention. As I mentioned, no, we're talking about the level curves. So what is Lagrange multiplier? I want to find the optimum for a given f of x y equal to something. Okay, let it be some k, something like, I'll show you that thing, subject to some constraint. Since time is there, I'm just running. I'm just talking about important thing. See, I'm having some level curves. Okay, I want to find the optimum of this maximum minima of with respect to some constraint. This is my constraint. So at this point, I can clearly see the tangent is common. There's a common tangent. This constrained curve and the level curve has a common tangent. So they'll be having a parallel gradient. Okay. So I can write del f. Suppose this is f. This is g, means I can write del f equal to lambda times del g. Okay. So del f equal to lambda times del g. So if you solve that system, you'll be getting a system there together with the constraint, then you can find the maximum minima. Okay, del f, see del f equal to lambda times del g, and together with the constraint, if you solve the problem, then you can find the maximum point. So this method is Lagrange multiplier method. Okay, already in optimization also we'll be using this Lagrange multiplier, but the idea is it's based on the level curves. Okay, and the curve, the other curve meets the level curve, they both have a common tangent, which implies they have the same normal there. That means their gradients are parallel. Okay, so with this idea now let me go to the code. Okay, so I'm going to find the maximum minima for this function y square minus x square on the ellipse x square plus 4y square minus 4 equal to 0. So I'm going to find where the maximum value and minimum value happens for this function on this particular constraint. So what I've done, I know sims. What is sims? People might ask, because it's very similar to what you do in other languages, int, float. Okay, here I'm defining those variables to be symbolic variable. So to do that, actually when you want to do in your system, you have to have the symbolic toolbox. It's another toolbox called symbolic toolbox. So when you are using diff, all this symbolic toolbox is needed. Okay, but here I don't need anything. I'm just using sims x y, and I'm going to find lambda, because I'm going, my unknowns will be x, because I'm doing for a 2-dimension case. It will be x, another unknown will be y, and another unknown will be lambda. Okay, then real, we know that if you'll be finding maximum minimum only for real values, not for complex values. So real, and I'm going to give f, I'm going to give what is g. Then I said no, we have to solve the dou f, that is dou f equal lambda dou g. That is done using Jacobian. Okay, I'm finding the Jacobian, or I'm going to find Jacobian with respect to x, y, and lambda. So that is stored in your J. Then using that one, I'm going to plot this. Okay, let me run this one, because I have to give the input from keyboard. It is y square. So enter the function y square minus x square. Okay, and it is, my constraint function is x square plus 4 star y square y cap to minus 4. Okay, see, it finds it. So here 4 critical points are there. See, if you solve this, you'll be getting ax equal to minus 2 by 2 0 0 0 0 minus 1 1. So the points will be this is lambda value. This is minus 2 0 will be 1 point, 2 0 will be other point, 0 minus 1 0 plus 1. Okay, now see, we'll see the 4 figures. Okay, so this point is minus 0. So this is the ellipse I'm talking about. This is the level curves for this particular function, level curves. So this is the constraint. Okay, this is where the optimality is reached, but there's, don't think there is no level curve. Lot of level curves will be there in between this. Okay, since you're not able to visualize that, I'm just drawing for this. These are level curves. In between, lot of level curves will be there, because from 5 to 6 I can write any number of points, no? So lot of level curves I can draw for f of x equal f of xy equal to 5 to f of xy equal to 6. So it will be f of x equal to 5.1, 5.2. So a lot of level curves will be there. So this is going to be my one maximum. Okay, that is -2, 0. Next one is 2, 0. See, 2, 0. This is 2, 0. Then next point is, this one is 0, -1, 0, -1, and another one is 1, 0. Okay, so this is the way, if you use the Lagrange multiplier, we can easily visualize these are the level curves, and this is the curve, how it happens, and how the optimality is reached with respect to the given constraint. Okay, so now I hope you understood little bit from this, because it is not easy to tell everything in 2 hours, because to explain the code, that's why I didn't explain the code. And another important thing is maximum minimum for a surface. We have discussed maximum minimum for a function of one variable. Now we'll be going for a surface. Now for a surface, we know the idea is I have to find d. What is d? D is fxx into fyy minus fxy whole square. Okay, so that is my d. Okay, see here, fxx I'm finding. How to find fxx? From fx I'm differentiating with respect to x. So I'm using the command diff. What is fxy? Fx I'm differentiating with respect to y, that is fxy. Fyy, from fy I'm again differentiating with respect to y, that is fyy. So I'm having all the three, I'm finding this d. Okay, d, some book they use ac minus b square, ac minus b square, that is nothing but your fxx, or you can think of a determinant fxx, fxy, fyx, fyy. So if you expand the determinant, it is fxx into fyy minus fxy whole square. Okay, that is your d. So based on the d, if your d after substituting the point of interest, because once you solve this, you will be getting the critical points. You substitute the point here. Based on the point, if your t1 is 0, then we need further investigation. If it is less than 0, we know it is a saddle point, and if it is less than 0, okay, that means t1 is greater than 0 and t2 less than 0, then it is a maximum point, and otherwise t1 greater than 0, t2 is also greater than 0, it is the minimum point. Okay, so we have this thing as a standard thing for our function of more than one variable. Now let me run and show you as the last program, this one. Okay, what is the function of my interest here? Function, I'm going to give the function, this one, is it? Let me copy this. Okay. Let me run this again. I'm copying this. Here I have to put star, otherwise you will get error. 3 star x cube y star. Here is star, 4 star. Multiplication I have to put star. Okay, this is my function. Saddle point, everything it finds. See, this is a surface. First surface, there's one point. My maximum point is there. Here, if I rotate this, I can find one saddle point at the top, at the bottom. Sorry, at the bottom, I can find one saddle point. So if I rotate this, I can find one saddle point at the top, bottom. Because if I go inside and check the command window, okay, I can see the point xy -1 -2 is a saddle point. -1 -2 will be a saddle point. Okay, that means an equilibrium point. Okay, where is neither maximum nor minima, and -1 -2 is a minimum point, and value is -10. So that will be a minimum point, value is -10. Okay, So I think I can stop with this. Okay, I hope I have kindled a sort of interest in visualizing your mathematical concept using MATLAB. Okay, if you visualize an idea and learn, I think it will be very useful for you to understand how it works. That is the way we have devised the syllabus. The seniors have divided the syllabus in such a way that everything is done visualization. Even in R, whatever they're studying there, they're visualizing using R.